Or oftentimes doing what we call a u-substitution will allow us to integrate a bunch of different functions that we were not able to integrate before, okay? So let's talk about how we can do that. The notation isn't really different, and you know, it's nothing that I'm going to have you guys, like, I'm not going to have you memorize like this definition or anything like that. But if you are, you know, integrating a function within a function, like to the left, this is when we would use u-sub in the past. So you would do your u-substitution, and then, you know, figure out your du as well too. That's all the same. The only thing that changes when we do u-substitution with a definite integral is that you also need to change your limits. Previously, on calculus, you would do a u-sub, and then you would get your antiderivative, and then you would plug your expression for u back in to get an answer in terms of x, okay? In this case, what we're going to do, we're not going to do that. We're going to do a u-sub, we're going to find our antiderivative in terms of u, and then we're going to evaluate it with new limits. The limits that they initially give you are in terms of x. They're just numbers, but they represent x values. So what we're going to do is we're going to change our limits to represent values for u and then evaluate it with those values. And then that'll just make it easier and take a step away, okay? So all we got to do is change our limits. So let's start small. Oh no, did I do the graphs again? Is it on every page? Just that first one? Okay. All right, well, either way. Let's start here. So I want to do a u-sub. We're used to u being the value inside of our grouping symbol. That's not going to change for this one. So we're going to start by letting u equal x squared plus 1. We take our derivative, 2x dx. We toss a half out in front, show that step, I suppose. Cool. And then I have what I need because there is an x in front of my grouping symbol, and then I can just toss a 1/2 in front of my integral. So 1/2. I'll deal with the limits in a second. So then x dx gets substituted. We're left with u cubed du. But what I would like to do is I need to come up with new limits in terms of u, okay? All right, so then I need to plug in my values, my lower limit and my upper limit. I need to plug those values in for x into my u substitution to come up with new values, okay? So the first one, I would get u equals 0 squared plus 1, which is just going to give me u equals 1. And then for my upper limit, I'm going to get u equals 2 squared plus 1, giving me 5. So then my new limits become 1 to 5, and then you just take the antiderivative. But the nice thing is you don't need to plug your expression for u back in, which oftentimes when you do your u substitution, actually every time you do your u substitution, it should be a simpler antiderivative. So it makes it nice. All right, so then we get 1/4 times the half that's already there, and then u to the 4th power evaluated from 1 to 5. And then we just need to evaluate. So 1/8, and then we would have 5 to the 4th minus 1 to the 4th. All right, 5 to the 4th, 625? Yeah, 25 squared, and then minus 1. So 624 over 8. '70s sound good. Tarun says 78. How are we feeling about that? It's got to be pretty close. Cool. Well done, Tarun. 78. All right. Let's do some trig. There's one similar to this on your test, and it did trip up a couple of us. So I wanted to put something like that in here. I'm going to go over it when we talk about your test as well, too. I think you did get it wrong. I can't remember.
Yeah, because inside was also.
Yeah. So I think I think it was just a very minor mistake. Got to do u sub. What are you guys thinking for u? Sine 2x. The trick lies in realizing that this is equivalent to 0 to pi over 8 of quantity sine 2x to the 5th power cosine 2x. You don't have to write that, but that is an equivalent expression. Once we write it that way, figuring out what u is much more obvious, but we've got to try to spot that ahead of time. So sine 2x, good. And then when we do du, what do we need to remember to do, Tarun? Yeah, or chain rule, right? You're fine. Function within a function. So we take the derivative of 2x, which would be 2. So we also need to have that piece as well, too. Okay. All right. So we're going to put a 1/2 out in front. We'll deal with our limits in a second. What is left over when I plug in u? U to the 5th. So way easier. And then I need to come up with an expression for my values for u. Okay, so I got to plug in 0, and then I need to plug in pi over 8, or whatever order I want to do it in. So sine of 2 times pi over 8, which is going to give me sine of pi over 4, so square root of 2 over 2. And then for my other value, I would have sine of 2 times 0, which is sine of 0, which is 0. One thing you need to make sure you keep track of is when you are doing your changing of your limits, that whatever value you plugged into for your upper limit still goes into your upper limit, regardless of whether it's larger or smaller than the other limit. I think you'll see an example of that here soon. So then this is going to be from 0 to square root of 2 over 2, and then we just evaluate. Du. All right, so 1/2 times 1/6, u to the 6, evaluated from 0 to square root of 2 over 2. So we get a 12th. And then we're going to do square root of 2 over 2 to the 6th power minus 0 to the 6th power. All right, so 1/12. Okay, square root of 2 to the 6th would be 2 cubed, right? So it'd be 8. So then we have 8, and then 2 to the 6 is 64. Yeah, so 8 over 64. So a 12th times an 8th. So 1 over 96, 96th. That's a really good question. Let's talk about it in terms of your test. Well, let's talk about it in terms of this. Don't need to put unit squared. I'm very glad you're thinking about this as area under a curve, because it's what an integral represents. But when we're using notation of just finding the value of a definite integral, you do not need to put a unit of measure with it unless I say find the area under the curve. So like in the problem itself, it gives you a context of area, then you need to put your unit of measure. I was a little lenient with that on the test. There were a couple problems where I asked you to find the area using geometric formulas. That would be a great candidate for unit squared. You know what I mean? All right. Cool. Another one. Hey, what's u? Okay. So then du is 40x. So we have a 4th. It's going to sneak its way in front of our integral. What would I be left over with inside of my integral? Good. U to the negative 1/2 du, or 1 over square root of u. So I need to find my limits. So then u is going to equal 4 times 2 plus 1, or 9. And then my other one is going to be u equals 4 times 6 plus 1, or 25. Oh, man. Those are perfect squares, which is good news for us here in a second. All right. My new exponent, I add 1, so it becomes u to the 1/2, positive 1/2. And then multiply that by 2. And then I need to evaluate that from 9 to 25. So I combine my scalar multiples, and I get a half, and then I multiply it by square root of 25 minus square root of 9. So 5 minus 3 gives me a nice, well-rounded answer of 1. Half of 2 is going to give me 1. That was satisfying. All right, we feeling okay? You guys did great with FTC in the past when I taught it to you guys the other day. So adding in the u-sub, I can't imagine it's going to make it any more difficult. There are 2 ways that we can solve this problem. Tell me what you want to do. U equals what? Okay. Was anybody thinking u equals secant x in their head? Because either one is totally fine. Let's talk about it real quick. If u equals tangent, what's the derivative of tangent? Nice. If u equals secant, what's the derivative of secant? Secant tangent. You guys see how I could break that up? Let one of those secants be u, and then I would have the derivative there. So it really just comes down to which function you want to evaluate with. But let's let, you guys said tangent first. So let's let u equal tangent. So then du is going to equal secant squared x dx. I have that. Super. So then let's change my limits. All right. So then my limits were 0 to pi over 4. So let's say top limit is pi over 4. So tangent of pi over 4, which equals, nice. And then tangent of 0. Okay, that's sine of 0 over cosine of 0, which is what? 0. Cool. All right. So then I just get the integral from 0 to 1 of u du. And it becomes the easiest integral we've done in a while. So 1/2 u squared, 0 to 1. So we get a half times 1 minus 0, which gives us a half. Okay. Yeah, I handpicked this one because it looks daunting, but it won't be bad. We're doing great. What do you guys want to let u be? Derivative of that? Good. 1/2 x to the negative 1/2 dx. Do I have that? Yep. Good. Got the business end of it. And then we can just toss the 2 to the other side. 1 over square root of x if we really want to pick out those pieces. So we've got the dx. We've got the 1 over square root of x. So that's really good. Cool. Let's figure out what my limits are. All right, so then u is going to equal 1 plus u, and then we would have square root of 9. So 4. And then for my lower limit, 1 plus square root of 1, which is going to give me 2. I've got a 2 in front of my integral. My limits are from 2 to 4. What do I get inside of my integral when I do that u sub?
U to the negative second.
Yeah, u to the negative second, 1 over u squared. Any questions how that all comes together? Okay. All right. my new exponent becomes to the negative first power. So I'm going to multiply by -1. There's also that 2 there. And then we evaluate it from 2 to 4. So -2, 1 over 4 minus 1 over 2. So then -2 times -1/4 gives us +1/2. Feeling okay? Cool. Man, we rolled through that lecture pretty quickly. Let's do one more. This is a good one, though. There's a couple things that are going to go on in this one. What are you thinking ahead of time? What are you spotting ahead of time? Yeah, so we're going to have to do u-sub, and then we're going to have to do change a variable. So then u equals 2 minus x. du is negative dx, so we've got to keep track of that negative. But Ashley's spotting, okay, well, I've got that extra x minus 1 that's there, so I need to solve for x in terms of u and then plug that into my expression. So if I do that, I would get that x equals, I'm actually gonna write this down below. But if I do that, I get that x is going to equal 2 minus u. So I'm going to have to plug that in. So when I do that, negative integral, I'll take care of my limits in a second, because that's going to be a separate conversation. So then x is 2 minus u. So then I'm going to have parentheses 2 minus u minus 1. And then multiplied by that, I would have u to the 1/2 du. And I'll simplify that in a second. Let's just take a second to plug our things in first. Any questions where any of those pieces came from? Okay, let's talk about limits before we simplify this. So for my limits, I adopted this notation in my teaching career today. But it's important that you keep track of like where each limit comes from. So like for the top limit, I need to plug in 2 for x. So if I do that, I would get u equals 2 minus 2, which is going to give me 0. And then for my lower limit, I would get u equals 2 minus 1, which is equal to 1. So here's the mistake that I'm trying to avoid. Typically, our upper limit is our higher value. But in this case, our upper limit gave us 0 and our lower limit gave us 1, which is different than how we usually write our limits. We're used to the larger value being up top. So I don't want to have you guys make that common mistake. So that's why I'm going to use that notation to when I rewrite our limits. Okay. All right, but I'm making a big deal out of the limits. What can I do if I want to orient them in a way that's better for us? Yeah, so flip it, right, and then make it negative. There's already a negative in front, so it's just going to take care of that and make it positive. Cool. So I'm going to make this a positive integral from 0 to 1, and then we simplify the inside. Okay? Everyone with me? Okay, cool. So then on the inside, we're going to have 1 minus u, and then let's do it in steps, it's fine, and then distribute u to the 1/2 to both of those pieces. So that's going to give us u to the 1/2 minus u to the 3/2. Du. And then we take our antiderivative and we evaluate. I'll move back over here. All right, so then u to the 3/2 is what our first term will be. So let's multiply that by 2/3. And then minus u to the 5/2. So let's multiply that by 2/5. And then evaluate that from 0 to 1. Cool. So we plug in our values. which is for the first one, 2/3 minus 2/5. And then minus, conveniently, if I plug in 0, I just get 0. So 10/15 minus 6/15 gives us 4/15. Cool. Feeling good? Yeah? All right, super. Homework is on the last slide. You guys have plenty of time to well, I'm going to give you guys your tests. We'll talk about those. But then other than that, get started on your homework. And then, again, quiz Thursday, tomorrow, on fundamental theorem of calculus, u-substitution, and then, so u-sub with fundamental theorem of calculus, and then total area. So again, when we talked about area, Tarun brought this up earlier, your integral is just going to represent area under a curve. That's what we call our net signed area. If I want my total area, what do I need to put on there? Absolute value. Oftentimes what that looks like is splitting it into two separate integrals, just finding where that domain breaks, and then evaluating each one. What's up? Do you have a question?
Do we get a calculator tomorrow?
Do you want a calculator tomorrow?
I don't know, do we need one?
I don't know. I don't know. Yeah, you can have one if you want. Doesn't bother me at all. Red calculator it up. Cool. Not a graphic calculator though. Just a red one.